Good afternoon. Welcome to the Distinguished Lecture Series. Today is a big day for Carolina, as we can see all the blue T-shirts, and also we have not one but two big events. It's a great pleasure for me to welcome Professor Dave Patterson, a chair professor from computer science at UC Berkeley. I was thinking of how to introduce him, and I realized Dave Patterson needs no introduction, right? No. And he has an amazing things, and I guess the best way to summarize, maybe like an attempt, a lot of things he's done over 30 years impact our life every day. The work he did in the early 80s on RISC computing changed the field of computer architecture and compilers. If you want fast disks, he worked on RAIDs. In the late 80s and 90s, he worked on building high-performance computing with network of workstations, which all the internet service providers use, into what's becoming a cloud computing. And if you think his research accomplishments were not enough, a whole generation of computer scientists for the last 20 years have learned so much from the books he did with John Hennessy and Patterson Hennessy. Most have a copy of that. And besides doing great research and education, he was also a chairman of computer science at UC Berkeley. I was fortunate to be the student at UC Berkeley at that time. He has been the president of CRA, president of ACM. Do you ever sleep, Dave? So it's not surprise. Dave has received more than 30 major awards, including member of National Academy, Silicon Valley Engineering Hall of Fame, IEEE John Van Neumann Medal. And today we are very proud to have him here. He's going to talk about a problem which a lot of people is thinking is the biggest challenge computer science is facing. That is a parallel revolution. He's going to talk about the problem and I guess tell us, are we the good guys or the bad guys? Without further ado, let's welcome Dave Patterson.
Thanks for the generous introduction. Yeah, so at MIT, they asked me to fill out a survey, and they said, what is the one trait that you wish you had that you don't have? And I thought about it a long time, and it was sleeping soundly was the one. I would really like to sleep soundly. I think part of, at this point, once you've put 30 years into a job, you're starting to realize you're closer to the end of the beginning. I think the thing reason I got a lot, because I'm surprised that people say, wow, did you ever sleep? And I think that actually I kind of woke up one day, and I don't know why, but woke up one day and I realized, it's the number of projects you finish, not the number of projects you start. I mean, that sounds like a Fred Brooksism, right? But I just woke up one day and realized that, and so ever since I recognized that, what I do is I have wider time slices. I don't try and do 1,000 things, right? I said, well, to finish things, I have to add dedicated time. So I tend to finish most of the things I do. And so I think that's the difference between me and most faculty. Most faculty start 1,000 things. I don't finish that many, but most of the ones I try, I finish. So that's my words of wisdom. So I'm going to tell you today about just a remarkable thing that's going on in the field. Just remarkable thing. The way I introduced it using a different sports analogies from football is what's going on in the computing industry today is a Hail Mary pass. Right? The computer industry is stuck. They just took the ball and threw it as far as they can. And for those of you who know football, it's a lot easier to throw a Hail Mary pass than to catch a Hail Mary pass. So that's what we're in right here. Just if you think in the historical context of computers in the industry, a problem that people have long thought would be a great thing for us to work on. And just because it's been important, I've been on 10 projects in my career. This is my third parallel computing project, right? We keep trying and not succeeding, and now the whole industry is bet we're going to succeed this time. It's just what an amazing time that we live in today. So I'm going to tell you about that. And so I've got two pieces of the talk. I've got kind of this broad brush describing what the problem is and what some of the things that we're doing at Berkeley, and then I've got a more in-depth thing on a model of computation. And so I'll pause and the general questions, and then if you stick around, I'll go into some more depth on the parallel computing model. And I think I just said these things. So why are we here today? Why did this happen? Basically what happened is we ran out of power. Is that there have been these scaling factors have been going on, but slowly but surely the power per chip is going up. And once it got to about 100 watts on a chip, that you could stick in a laptop or something like that, you can economically cool 100 watts. And you could figure out a way to cool 200 or 300. It's just a lot more expensive. So they basically ran into a power wall. And this was a surprise. It's a surprise that it's a surprise, but it was a surprise. To give you an idea of a surprise, this is what's called the International technology roadmap for semiconductors, and they plotted all kinds of things. They've been getting together since the 1990s. They got together every 2 years, projected what to expect. And according to the 2005 roadmap, we're getting rid of our 13 gigahertz processors, thinking about buying our 15 gigahertz processors next year. And 2 years later, the same group, the roadmap went down, right? So something happened, right? And you kind of talk to the people because it wasn't that nobody predicted power would be a problem. They just had faith because in the semiconductor industry, there'd always been these walls like line widths and stuff like that that you couldn't possibly cross, and somebody had already figured it out. And they just thought at the last minute, like in the next couple of months, somebody was going to solve this problem, and the clock rates were going to keep going up. So that didn't happen. Clock rates could not go up. Power really was a limit. So what this switch to multi-core is not because there was any kind of programming breakthrough or anything. It's just that it was easier to build multi-core than it was to figure out a way to build 15 gigahertz processors that are 100 watts. No one could build that. And trust me, if somebody could build a 15 gigahertz 100 watt processor, there would be a gigantic market for it because the parallel challenge is amazingly difficult. So what happened really is what else could they do, right? They want to keep offering more performance. The only hope was more power efficient cores, and that's where we're here today. And this is a huge sea change for the whole industry. And, as whether or not, I'm using, you guys probably don't recognize, I'm using the terminology from the 1960s. The revolution has started, are you part of the problem or part of the solution? So, look, has the revolution started? It has started. There's nothing you can do about it. All these companies who build microprocessors, they've got the next 5 years of plans. They're already shipping more multi-chip, multi-processor systems and single processor systems. And so it's happening. It's not something you get to vote on. People say, parallel programming is hard enough as it is. Parallel programming is going to be harder. I don't want to work on that. Well, as long as you don't want faster programs, that's fine. If you're perfectly happy that your program, as it is right now, doesn't need to get any faster, fine, you're set. If you want to add new features, if you want more functions, the only way you're going to get that is parallelism. And unlike, like I say in the slide, it's not controversial like evolution, right? I know that's controversial in some parts. Well, is it true or not? Look, I don't know anybody in the computer industry or in academia and architecture that doesn't think that the only way forward is parallel computing. I have not met anybody like that. So it's happening. So the context I'll give you is a bunch of us started, it actually turned out while I was being president of ACM, I took a sabbatical so I could do that job well, but I had some extra time, so we started getting together and talking about these issues, and a broad group from lots of backgrounds mentioned here, trying to understand what the implications of all this were. And this eventually led to a report that we published a few years ago giving this Berkeley view on parallel computing landscape that was pretty widely read, and then that led to this parallel computing lab. And more or less, the amazing goal that seems obvious of what the industry wants, and it's hard to imagine we're going to deliver, is to make it productive, that it's just about as difficult as sequential programs to build parallel programs. If they're going to be efficient, that means power efficient and high performant. They're going to be at least as correct as sequential programs, and they're going to be portable, a long-standing challenge for parallel computing, that you'll develop a program and run on one multi-core and you'll be able to port to others. Not only all that, but as the number of cores increase, but they're going to increase every 2 years, it'll keep increasing in performance. And that's what we have to do. That's the challenge that is presented to us as a community to address, otherwise the industry is going to be in trouble. And wow, what an amazingly difficult set of challenges. So what's the context that okay. Something, was that the wrong challenge? Okay. Okay. Easy problem. So the context that we think of it as being, is the two extremes of computing is kind of this Berkeley view of what's the future, and I think lots of people think that way today. Is at the one extreme is these warehouses, these data centers of computing, which in popularly referred to as cloud computing, where they're the biggest computer buildings ever built, where computer architecture and civil architecture meet, right? Is these warehouses of buildings. And at the other hand are these things, battery-operated devices that we carry with us. And so that's what we think is these two extremes are where this technology is going to be deployed. And we're already seeing things besides the iPhone, which how many people have iPhones? Yeah, it's remarkable it makes you realize what these things could do. And now there's this new device that they're calling a netbook, which is an even smaller operated thing. So I think battery operated things at one hand is one setting set challenges and the data center is the other. And so these are for the future client, and the data center is the future server for client-server computing. So our approach with the PAR Lab has these 5 pieces. And this is our colorful version of it, which you'll see it later. The purple stuff, applications, we're really serious about applications. As the director of PAR Lab, I'm familiar with our budget. We're spending at least 20% of our money on applications. So it's not like classical computer science where, the project's over, better get an application. Well, there's a sophomore. You do the medical app, okay? And the last 3 weeks of the project, right? No, this is really right from the beginning, real experts in these areas, and I'll tell you about that. We think of it having the software challenges, which is the center of the challenge here, is having these 2 pieces, which we call a productivity layer for most programmers, efficiency layer for the experts. And then the job of the operating system and architecture is to help. We're there to help. We're not setting the agenda. Correctness is really important, and parallel computing has a lot of challenges in that. I'll tell you about some of those results. And then the yellow column on the left is diagnosis. How can we reflect back up, measure and reflect back up through all these layers? And so interesting question here is, what's the big idea? It's kind of interesting that in a research project at the very beginning, a question you should ask is, what's the big idea? Because you might think that the right time to ask that question is later in the project. But if you actually look at the history of parallel computing, the big idea was at the beginning. It was like SIMD computing or data flow languages. The answer was at the beginning of the project. And the job of the project was to prove that answer was correct, right? But we're actually not doing that. We're saying this is an important challenge. We've got a lot of interesting ideas. The applications are going to help determine which ones are the big ideas. So we'll be working with these application experts, designing something that would help them get their job done. And hopefully, if they can get their job done, then other application experts can do it. And at the end, we'll figure out which were the back ones. So after the project is over, we'll be able to figure out what were the big ideas rather than in advance. And it was just kind of interesting to me when I heard questions, but you haven't told us a big idea yet. Well, it seems like we ought to figure out after we get some evidence what the big idea is. So as kind of remarkable, so what we did was we thought about what applications to be, and we wanted to find people on the campus who really were desperately needed more computing or computing in a smaller form factor, and tried to get a mix of them. And kind of to my surprise, one of the first ones, and our possibly most enthusiastic applications expert was in music. So I never thought music was that big a need of computation, but they're as insatiable as our graphics colleagues here. Not only did they want a lot of computing, they have this real-time or soft real-time demands that's serious, is that the human ear really can tell when music is off a little bit. That's not like if you go to your kid's orchestra, that's not a wonderful experience. And why is that? Oh, the music's not so synchronized there, right? So we don't enjoy that. The beautiful music has to be very carefully synchronized. And David Wessel, who's actually in the music department, but a big advocate of what we're doing, a place he used to work, if you hear clicks during the digital performance, he said 3 clicks and you're fired. That was the kind of the rule of their institute there. So they really have a very high quality. The things he's think of, this is a picture of a 3-dimensional loudspeaker, 120 tweeters on all sides. So you can imagine we need to have this in our own homes to recreate the symphonic experience there. It turns out that some of these things are close to the same technology need for hearing aids. Many of us who are more senior, over the fullness of time, need help with hearing aids. Some of you who are much younger, who use iPods, need hearing aids really soon. So hearing augmented, imagine your cell phone helps your hearing aid work better. Wouldn't that be an interesting technology? And then I think everybody in the music department is not only kind of interested in music, they're all performers. So he's rebelling against the constrictions of a keyboard or guitar strings. He wants to have a novel interface, a touchpad, that depending where he on something this big, where he presses, how deeply he presses, he gets different musical experiences. He wants more innovative applications, more innovative user interfaces, really, to perform beautiful music. Another one is health, another app. We have a person who's in the bioengineering department, but also in the UC San Francisco Medical School. And the application of, basically it was an area of let's take advantage of body scanning and then tailor something to an individual. And he went through a few of them, and he decided recently to go with this one, which is a stroke diagnosis and treatment. And again, for those of us more with a lot more experience in the field, we think this is just a great thing to work on. It's the third leading cause of death in the United States. And apparently the way it works is either if you have a stroke and go into the emergency ward and it's been 3 or 4 hours since they think you've had your stroke, they just leave you by yourself. That's the modern medical theory. So wouldn't it be nice is if we could get patient-specific, based on a scan, 3D simulation of both the arteries and then the blood flow in that, which apparently those haven't been gotten together, to get an idea what's going on. And particularly, he recommends looking at what's called the Circle of Willis, which is, if you can, I'll just point at it. This is the Circle of Willis here. And it turns out it's called the Circle of Willis, and that applies to about half of us in this room. Half of us actually have a real circle, so if one part breaks, there's another way the blood will flow, and the other half, it's not a full circle. So that's about 80% of the life-threatening strokes, and what we really like to do is make it possible to do highly accurate simulations near real time, so that if the stroke happens and it's been more than 3 or 4 hours and we get there, the surgeons could see, or the doctors could see what's probably going on, and then see if they could come up with one of the blood thinners or other things that they do for strokes that would apply. Would it be more dangerous, do no harm? Would it be bad to give them something, or would it be helpful? So that's the health app. But I think there's lots of health apps that would be interesting to do. One that's more fun is that if those of us who have iPhones realize you could have tens of thousands of images, and how would you find the image you're interested in? And this is a query by example using photos to find things. In this case, it's a mother and daughter photo. Here's separate pictures. Can we find the one with them together? And using machine learning and support vector machines, that's the mechanism of training and trying to be able to find something. But an image-based one. Speech, of course, that's a long-standing challenge to the computing people that are involved in. We have a local expert who is interested in speech in rooms like this, and his idea, he calls it a meeting diarist. Wouldn't it be wonderful you go to this meeting where everything that occurred that meeting was written down by speaker, so that we said, gee, I remember Dinesh said something really important, and I can't quite remember what it was, and you could go and find the speaker and find the section of the meeting that you would do that. So these have all been media-oriented, so we decided that we should have a fifth one that was more computer science-y than more media-oriented. And so we think about the parallel browser. So if you think about the Web 2.0 ideas of software downloading out of the cloud onto your computer, that's done in a scripting language, a JavaScript typically today. So there's two ideas there. Can you do things to make browsers run a lot faster with a parallel handheld device? And also, could you make a parallel language so that anybody who's building a Web 2.0 app would be implicitly doing parallel programming? So those are our 5 apps. So if we could do those, then as director, I can come up with what I'd like to do with technology. And what I'd like to do with technology, I call name whisperer. That based on our image retrieval, is that what I would like is this handheld device, sitting in my pocket, and then when somebody comes up the audience, glad you remember me, and then I could say, well, yeah, that's Dinesh. I remember in 1980 you took 252 from me and you got an A-, and if you'd worked a little harder, you would have got an A. And absolutely, if there was a new computer and the doubled number of cores every year, and it would help me with my memory and recognize faces, I would absolutely buy the latest one that comes along, so that supplement my memory. I would absolutely love to use that. And the thing to say about this is I don't know if any of these applications are going to be the killer applications, but I think, in our thinking about this, to make people want to have more computing cycles, it's not really the case that you have to make every single program in the world run faster and scale. So I'm pretty happy with Word just the way it is. That's okay. So I think in the future, I would still probably want to keep using Word. But what we need is a few apps that cannot get enough cycles, a few apps that you love using that goes ahead. So as long as there's some applications that need tremendous computing cycle, that would be success, rather than every single program in the world has to become parallel. So this is a little bit easier problem than the past way parallelism has been characterized. But so maybe that's a little bit more reason to be, optimistic, to be, well, maybe it's a solvable problem. All right, so that was kind of what the apps are like, which are really driving the project. So what should we compute? So we spent a bunch of time on that in the Berkeley View report. And there was this provocative statement from the high-performance computing community that is widely accepted, that there were 7 numerical methods that will dominate high-performance computing for at least the next decade. So I was excited to hear that, because 7 is a number you could wrap your mind around if you were a computer architect or if you were a language designer. 7. So we looked at a bunch more applications besides high-performance computing, embedded, desktop, databases, games, machine learning, computer-aided design. And we kind of doubled the number of these numerical methods. But we were surprised, that now it's more like a dozen or so. So that's not that many. You can kind of wrap your mind around that. And then when we had that list, so did it work with our applications? And as we went across these 5 applications, more or less we found them. So this is a temperature chart with red being really important and green being not so important, yellow mediate, and blue not important. So nobody needed all of them, but all of them were needed by somebody. So this idea, and I think this is one of the bets of the Parlab, is that we are going forward with this provocative claim that there's a small number of things that can be found in most programs. So that if you're going to invent a new computer or a new programming language, our advice would be, you better be able to do these well, because programs are going to do them. Now the data types will change. High performance computing is almost all double precision floating point, but the same things could happen, applications embedded, which could be 32-bit integers, 16-bit integers. The data types would change, but these are things that are fundamental that we think are going to happen a lot. So that's one of our provocative bets. The other provocative bet is that if you look at there's something about the history of computer science, and maybe Fred Brooks could explain why this is true, is we seem to have faith in any problem is solvable if we just have the right programming language. There's something about our field that the reason we have any problems, the only problems we have in computer science is because we just haven't invented the right language. Once that language is invented, all problems will be solved. And particularly in parallel programming is that approach. So we're not really making that bet. This is a different one. This is architecture matters. Software architecture matters. So there are some well-known patterns. Now this language comes from actually a Berkeley civil architect. He wrote this book that tried to capture everything that had been learned in civil architecture for 2,000 years and put it into a single book so that he would make it all fit together. He called it a design language. That is, everything from designing cities to designing roof caps was in his book at some layer of what we would call layer of abstraction. So this is inspiring. So we're talking about design patterns at a pretty high level. So at the top of this slide, so model view controller, which is one people have heard about in the Ruby context, Ruby on Rails context, and Python killer. So the idea is that if you don't have a good software architecture, and there is a lot of software in this world that does not have a good software architecture, you have no chance, right? If you don't have any architecture or it's a lousy architecture, the question isn't whether it's going to be parallel or not. The question is whether the program is going to work at all. So, and then the contrary thing, by having a really good architecture, that will make it easier to unveil the parallelism. So we're betting on software architecture, software engineering ideas rather than language ideas is one of the bets that we're making here. And we're working our way through that, and we think there's a relationship between what you're computing and what the architecture of how you design your program, and that those things will be correlated. And then we need to go further layers down into the system, and we're not as confident about these lower levels of this, right? But we're attacking it that way. So we're really seriously driven by applications, and we've got these 5 apps, and we're betting on these dwarfs and design patterns as the guide. As I said right in the beginning, when you have these just arguments about what do programmers want, especially if you're in computer architecture operating systems, it's a very hard argument. It's a little bit easier argument if you say up front there's at least 2 types of programmers. There's the efficiency layer programmers. They really want bare metal efficiency. They're the type of people who can graduate from Berkeley or UNC with degrees in computer science that really understand what's going on, this kind of ninja programmers. So that's one type. And then there's the rest of humanity or rest of programmers that maybe they're domain experts. And so by keeping that in mind, you don't try to ask what the average programmer wants. You try to ask, well, what are each of these 2 types of programmers like? And so what we're shooting for is really good efficiency for the efficiency layer, and then reasonable efficiency, but really good productivity at the productivity layer, nevertheless. And hopefully, the productivity layer people will be able to leverage what the efficiency layer people build. And that's the approach we're taking. And the correctness area, again, lots of difficult problems in sequential software correctness. This is being inspired by a mixture of verification and testing. You verify what you can and what you can't. You direct the testing, and I'll give you some recent results on that. So at the productivity layer, we're going to restrict what you can express so that you just can't express some of the concurrency errors that are commonly plague software. And then at the lower layer, this mixture of verification and directed testing, automated directed testing. So verify what you can and then figure out how to test what's there. And I'll give you some examples about that. What about compiling? So we've been, and others have been, big fans of what's called auto-tuning. It's more search-based. So let's take one of these kernels or dwarfs that I talked about, and we're going to run that on a particular architecture. Rather than thinking of it as just a static problem, why don't you look at the particular machine you're running on, how many cores, what it's networking like, how much memory bandwidth, and tailor that low-level software to exactly that piece of hardware. So in a specific example with this temperature chart, this is just for dense matrix, which you'd think would be pretty straightforward. On this particular computer, the question is how do you block it? That is, what kind of size chunk do you try and compute on before you go to the next chunk? And the numbers of rows and columns for this particular computer, by far, it was 4 rows and 2 columns, and I can't imagine any way you would have figured that out in advance without doing the experiments. So and this has been widely used for sequential programs. These programs at the bottom have, for many years, been using this kind of auto-tuning approach to get the best performance. We want to do this for parallel programs. All right, so auto-tuning, productivity efficiency, and these libraries and frameworks to leverage. How about the operating system level? Well, again, we're here to serve rather than we're here to dictate. So from the hardware solutions, we think small is beautiful, that we think the kind of the many-core approach makes the most hardware efficiency if we can program lots of cores. That simple 5 to 9 stage processors, vector units, things that are both transistor efficient and energy efficient. Now, a lot of what's gone on in computer architecture the last 15 years has been neither transistor efficient nor energy efficient, because the job for the computer architect was to make things fast, but don't change the programming model. This is what we're doing today is kind of the third rail of computer architecture. Really efficient hardware, but you have to retrain all the programmers in the world, right? But if you can retrain all the programmers in the world, probably a lot of simpler things would be the best use of power and of transistors. One of these ideas, the weird place we are today in programming is people, to get performance by auto-tuning, they try to reverse engineer the caching system. Well, the original reason caching was invented by IBM many years ago was to simplify the job of the programmer. And the cache system will just hide all that complexity from the programmer, and life will be good for the programmer. Well, today, to get good performance, you have to reverse engineer. That's a weird spot of technology. So why not have it reconfigurable so it can act like a predictable local store when you know what you're doing, and act like a memory hierarchy when you don't. And then we're really focusing as single socket systems, all, hundreds of cores in a single socket. Well, if you talk about a single socket thing, you can talk about rapidly dividing things up into different partitions for security reasons and sharing reasons, and having very fast barrier synchronization if it's all on one chip. From the operating system side, these gigantic monolithic operating systems probably aren't the ways to go to the future. So deconstructing operating systems, use of virtual machines, that this is a popular idea both in the data center, and we think it'll make sense on cell phone side things as well. One of the questions today, when it costs millions of dollars just to create the mass for a chip, how in the world can the universities demonstrate ideas convincingly? Because it seems chips are going to be too hard to build. So we can do simulators, and that's what a lot of people are doing. So we're very excited about the potential of field programmable gate arrays. Because they have somewhat as flexible as software and pretty easy to change, and a lot like hardware in terms of design and speed, we think that pliable media will be a great media for exploring computer architectures. So as a demonstration system, we built a 1,000 processor system out of boards that have FPGAs on them. And this so-called RAMP project, which stands for Research Accelerator for Multiprocessors, which is a consortium of about 6 universities and involves Microsoft and Xilinx involved, as we're building a common hardware platform and common gateware to be able to all share this, help develop this architecture and accelerate the rate of progress. And so many universities are doing their own things there. Recently, we have this one was called Ramp Blue, which was this 1,000 processor thing. A recent result was one of the graduate students of the project, Zhangxi Tan. His insight was, you look at FPGAs, what do they do well and what do they do poorly? Well, what they do well is RAM, in part because it's the same RAM, and basically what a field programmable gate array is a lot of little RAM that you program to tell it what to do. So RAM is really great in this technology. Multiplexers are really terrible in this technology. You have to build a multiplexer out of RAM. So then if multiplexers are hard, he kind of asks, geez, why are we doing pipelining? So, and if we're trying to do lots of cores, isn't there a better way? So his idea, which he's got working and we call Ramp Gold, is to take a standard instruction set. Unfortunately for the Ramp Blue, we used a instruction set that was invented by Xilinx, so that almost no software uses it. So let's pick a standard instruction set, add a timing model, because field programmable gate arrays are like hardware but a lot slower than real hardware. You could get the wrong results if you use really fast DRAM and really slow logic. So a timing model, like you'd see in a simulator, will allow us to adjust. We can pretend how, count time and pretend time and how long it'll take to DRAM, even though it would be really fast in real time. It can take a long time in our pretend time. So that'll be an important piece of it. And then his idea was, instead of a bunch of pipeline processors, let's just use a multi-threaded single one, that is lots of hardware threads per core, that which you do with a lot of RAM, which is good in FPGAs, and let's not even pipeline it. Let's just switch threads every clock cycle, go to the next one. So by doing it that way, he's been able to build a SPARC V8, runs all the diagnostics, boots the operating system, 64 threads in a single FPGA at 100 or higher than 100 megahertz. So this is a pretty interesting, so one of these boards costs, I don't know, $500, and pretty credible multi-core design, pretty fast enough that you can run real software on it. Not as fast as real software, but we can change the architecture underneath it all the time. So it's a pretty exciting step in this area. So how are we getting these experts to work with us, since we're kind of building these slow but interesting architectures? Well, it's kind of a multi-part bet, is that we're going to help them with their applications and run it on the fastest hardware in the world. And actually, because of our good relationships with some of these companies, we can even get computers before they've been announced. The only downside for them is this is what those companies are going to make anyways in standard operating systems. And then they'll help us because they care about their application supporting. They want it to run on lots of different hardware. They will also port it to Ramp Gold. And this will be the very innovative architecture and operating system one. But because they want it to run everywhere and we'll help them with the commercial stuff, they're willing to talk to us and help us with the more pliable one, even though it runs slower. So we think we'll be able to get the software applications of the future and innovate in architecture and operating systems underneath it. The last thing is, it's a very sad story about how poorly performance counters work on modern machines. They're kind of incomplete and inaccurate is kind of the average here. So how in the world are we going to get efficient software if we can't measure it? And so we think there's an opportunity to figure out a standard, like an IEEE standard for floating point, an IEEE standard for performance measurement in the multi-core era that would be common across all platforms. And we think this is an interesting idea, and that help not only program development, but at least as importantly, while a program is running, so that the scheduler can make good decisions, so the operating system can make good decisions. And so we're going to advocate that and implement it in Ramp Gold to show that it has value. So I've been giving talks like this for a while. What about some recent results? Active testing in the correctness area. These two students work in Koshik-sen. Of course, concurrency bugs are going to be a big problem everywhere. So their idea is to control the scheduler to try and force the scheduler to schedule things in a way that are likely to uncover bugs. So they do program analysis to see that this program is vulnerable, and then make the scheduler schedule things in a way that's likely to uncover bugs. So rather than you just run it forever and they show up once in a while, they happen much more frequently. And they've applied this to real code and the open source software system, Apache, Java collections, even the Java database connectivity layer that many people use, and found real concurrency bugs with this idea. So that's a real promising area. These two students have been working on this auto-tuning idea of trying to combine machine learning, using machine learning to explore auto-tuning. So this auto-tuning idea, you need somebody who understands the algorithm really well, understands the particular architecture you're on to help provide the space to search. By using machine learning, we're instead going to take a lot of information about different configurations and different performance metrics, and then find correlations automatically between them to help reduce the search space. And in fact, instead of exhaustively searching the space, which would take 6 months, you could do it in a couple of hours. And the performance is shown here in the bottom for an example running on a couple of architectures. That in one case, the blue one, which is the machine learning optimized, and the gold one, which is done by a human expert in architecture things, we were able to match the performance. And in the other stencil case, we actually outperformed the human expert, which we were surprised. We were hoping that we'd be as good as the expert and do it without needing the expertise in a lot less time, but we actually outperformed them. So that's another recent result. This last one is really surprising. I thought Linpac, dense matrix, that is a solved problem. There is nothing you could do there. People have been working on this problem for decades. Well, it turns out, kind of the secret thing, how can a million processor thing solve a dense matrix? Well, it's a really big dense matrix, right? It's a 40 terabyte dense matrix, okay? So, well, there's a lot of problems that don't need 40 terabytes. Their matrix is smaller than 40 terabytes. So Mark and his advisor Jim Dello recognized that for more normal-sized matrices, and given the performance limit, there's opportunities for innovation there. So they came up with a new way of factoring something like dense matrices and got real speed-ups on more modest-sized factors of 4, 6, or 7 against pretty good code, the Scala pack, widely used code. Last recent result is one of these application accelerations, trying to take advantage of all the ideas in the Power Lab and this ideas of software architecture and things like this. And in this case, it's the computer vision problem, particularly of the piece called segmentation, where you're trying to figure out what the object's there, and trying to use a GPU than a standard desktop. So one of our colleagues, Jitendra Malik, is one of the leading people in computer vision. And in places he competes in conferences, there's a quality metric where you have to see, a human being's this good, how close is your vision algorithm? And he gets, he's the current world record holder, but alas, it takes almost 8 minutes for every image. So Brian took a look at that, looked at his algorithms, talked to a lot of people in the lab about more parallel algorithms, and became an expert on GPUs in CUDA. And he was able to go do that same quality algorithm in 2.1 seconds. So that's a factor of 200 speed up. So this is these sayings that go back in computing a long time. Every factor of 10 quantitative is a qualitative change. So that's a factor of 200. And so Jitendra Malik, who's kind of pretty conservative English person who never exaggerates just about, he says, I think this is going to revolutionize computer vision. So the results are happening right now. Brian's paper, we're going to go to a computer vision conference in a few months. We'll explain why it's so much faster and how he did it, and then the results. But that could be our first big impact. So I think what I'm trying to do is, at this early stage, is entertain questions here, because the next part is going to go into more depth. But what we're trying to do, really applications driven. We've got this idea that design patterns and dwarfs are going to give us some insight what's going on. This two split, the efficiency layer and productivity layer. The betting on searching to generate code rather than static compiling. Let's do primitives for the operating system to help. This verification directed testing and performance counters. Okay, so let me pause there and start the questions, and then I'll restart. Question?
You mentioned it a little while ago, the major problem of retraining every programmer in the world. Similarly, they said that if they were to reorganize the keywords in the Dvorak, you could get everybody to type faster, but you'd have to retrain everybody 100,000 hours. Is that,
how can this be true? Right.
Yeah, I'm wondering if...
Yeah,
that's a good need for that to get that problem.
Yeah, so one of the reasons that I started going around giving talks is I heard that the Usenix community, they got together and they did a poll. And it sounded like they voted against parallel computing. They said, we thought it over. No, that's the wrong answer. We don't want to, operating systems are hard enough. We do not want parallel ones. We're against it. And they thought maybe that was the end of it. Right? That'll get rid of those hardware guys. So I just wanted to so I just wanted to say it's not like computer architects are advocating this position. I think, here's a good idea. Let's make everything parallel. If we can solve this problem, the world will be a better place. It's not like we're saying that. It's like, I just want to let you know, by the way, we've gone to, like the Yogi Bear thing, when you get to the fork in the road, take it. We've taken the fork, right? You may not realize it yet, But all the computers you're going to buy from now on are going to get increasingly parallel. And if you buy, so, and a very believable scenario, I mean, in fact, the way you'd probably bet is if everybody in this room wants their friends have 4-core systems, and they say they wait a few years and they're going to have a 16-core, probably you would say nothing you will use will be able to see the difference between 4-core and 16-core. That's probably true, right? That's really going to be bad for the industry if that's really true, right? Is if there's no reason to buy another computer unless you drop it, right? that's a really bad thing. So I feel because we're kind of an applied field and we've got this relationship, interesting synergistic relationship with industry, I feel as researchers, we're supposed to like hard problems. We're supposed to, oh boy, a hard problem. I have tenure. I can work on hard problems because I have tenure, right? Rather than I'm shipping a product. We should say, oh boy, industry needs our help on a really hard problem. And a really hard problem, if we solve it, will save at least the IT world, right? So the thing I'm trying to tell you is going forward, more or less, if you're doing sequential algorithms, those are slow algorithms. There will not be a big jump in clock rate. We will see the clock rate era is probably over, right? I don't know what it's going to be. The guys who were trying to predict the future said 8% per year. That may be optimistic, 8% per year, right? So the clock rate era is over, faster multi-core is over. So what are you going to do? Well, you could just make your, it's plausible, we were talking at lunch today, that there are so many layers of abstraction in modern software that you could just get rid of all those and go faster. So maybe you would just run on sequential programs more efficiently. Okay. Otherwise, parallel is the only way. So if you need faster computers, you want to solve harder problems than you can run today, the only hope is parallel. So it's not like, why should I do this? What's my return? It's if you're happy with the speed of programs today, you're okay. Now, if you do that efficiency layer, programming layer split, we need to figure out, I believe plausibly, we will figure out ways of, there's environments like, there's really wonderful programming environments are getting invented today. I've used Ruby and Ruby on Rails. Wow, what a highly productive environment that is. It's believable that on an environment like that, we could figure out a way to make that parallel underneath, and the programmers can be amazingly effective. There's, what was the other talk that we just had? Scala, this Java-based system, and Lift, a Ruby-like environment. Wow, if you haven't programmed in one of these systems, it's amazing how productive it is to program in these things. I'm hopeful that systems like that, which have a much higher level of abstraction, will lend themselves to parallel computing. In particular, it'd be kind of interesting as if maybe we worry, the problem with language is always in the past is you kind of judge it on single core efficiency, and you'd say, oh, I can remember, nobody will use Java, it's too slow. I had graduate students who you think time to graduation would matter, right? But no. I'm sorry, I can't use Java, it's too slow, I have to use C. Okay, all right. So I think, interestingly, going forward, maybe it'll be scalability. So if the single core performance is bad, but we can scale up to hundreds of cores, that's more important. So I believe in these programming environments are highly productive for the domain experts. I'm more hopeful there. At the efficiency layer, there's a bunch of really hard problems, and I think we as educators should be figuring out what we should be explaining to the people getting bachelor's degrees and master's degrees in computer science, so that they can figure out how to use those things. So it's not I'm here as, I don't know, Paul Revere is probably might be the right thing. The British are coming, right? There's nothing we can do about it. We can't vote against the British coming. It's coming. But there'd be real reason, I can understand people's skepticism, like, I've heard this before, or it's too hard.
So just to follow on, I think at the end is when you started to touch on my original thought behind my question, which was, how are we going to change how we teach? Because if we're teaching people Java and C++ at a bachelor's degree level, they're not getting parallel programming until their senior year, and by then it's kind of an elective afterthought. It's
right.
not.
No, I think this is the amazing time we're in, right? Let's see if I can figure this out. This is kind of, well, computer science education trails technology, right? But oops, we've been teaching, and probably still are teaching, assuming the 2005 roadmap is true. Right? We assume you're probably still, processors are getting twice as fast every year, and they're probably still teaching that way, and it's not true. So what have we been doing at Berkeley? So one of the things we've been doing, a bunch of people are doing, is I think one thing that you can do educationally to get people used to parallelism is MapReduce. It's a pretty, if you have a lot of data, you can run it on a cluster, you can get the personal experience of running it much faster using lots of computers, and it's not very hard concept to teach. All kinds of people can use it. So that's a thing that we're doing lower level in the curriculum, and we have right now toward, more like a junior senior class is really the nitty gritty efficiency layer stuff. But, that's what we're trying to do. I'm hopeful that all kinds of universities are going to be exploring this idea and sharing what works and what doesn't work. But we need to simultaneously save the industry and change the whole curriculum so that parallelism is a first-class citizen. What an interesting time to live in. And this wouldn't be so bad if we just didn't have 50 years of failure at doing this, right? There's all these dead parallel computer societies. A friend suggested we should do a photograph of all the computer mugs of all the companies that have gone out of business with the bet that parallel computing will solve all the world's problems. What an amazing time. Yeah.
So I'm pretty much all the way over on the domain side. I work in genetics and bioinformatics.
Uh-huh.
So there's a lot of really interesting algorithmic problems and things in there. But a lot of the programming is at a really simplistic level, right? So I think there's a big range in that when you say domain-specific programmers,
Right.
because there are domain-specific professional programmers and domain-specific sort of naive programmers. And I don't write compilers, right? So the things that I've had to learn to do to program are not, I don't think, any more difficult if you had taught me the parallel concepts as recursion and pointers, and some of the fundamental concepts don't seem to be that much different. It just seems to be a relatively different set. So when you say retrain people.
So it's the reason that might not be true is because about every decade computer science takes one more foray at parallel computing, and then that group kind of gives up and retrenches. And we make steady progress. It's not like nothing happens, right? But people have had that notion before. The problem is because we teach sequential programming, and if we just taught parallelism, everything would be natural. That just hasn't worked yet, right? There's an argument that human beings, even though their brains are naturally parallel, logically want to think sequentially. They want to say, you do this, and then do that and that. That psychologists would say that's a pretty natural match to human beings. They don't naturally think parallelism. Now, there's a style of parallelism that has had good success in domain experts, and that's what's called data-level parallelism. And you can think of this as like dealing with arrays, that my object is an array. I'm going to do array operations. That's worked pretty well historically. There's a style of computer called vector computer that's a good match to arrays, and boy, scientists could understand how vector computers work and were very productive in it. So there are some areas of parallelism, but there's some reason to be hopeful. In this MapReduce thing that I was talking about, you can think of that as kind of a data parallel thing. So if you can characterize your parallel application as operating on big structured data objects, there's some more reasons to be hopeful, and there's more reasons to think that we can teach in a way that it'll work. What people said in the past is, well, that's too restricted a programming system. There's a lot of things that are important that you can't express that way, so that's the wrong answer, right? But so I don't know I think a good challenge for campuses and for computer science departments is to figure out how to help not only teach their undergraduate students and graduate students, is how to help the rest of the campus cope with this revolution that's going on in a way that will make their colleagues productive in this new world. When lots of people are, there are some people still writing in Fortran, right? Or these Fortran routines that have been around for 20 years and everybody trusts them, and how can we help with that transition? All right, I'll rotate. Middle. Okay, Henry.
I'm fascinated by your application-driven approach, especially that you've taken a reasonable number of a variety of applications. I'm wondering, in terms of these 5, how many of the and there's a really great result that you were showing here about segmentation,
right,
which I understand and appreciate. And in each one of these, do I understand that what you do is you send off a couple of people who are really interested and to study with the application experts, and then try to take something that is already done and to do it faster?
Yes, it's kind of over the question is kind of, well, in each of those areas we have an expert, often outside our group.
Yeah.
And then how we start in the beginning, we're trying to have kind of these tall, skinny people who are pretty good at lots of things, work with them to do a prototype like like the vision example here. And then what we're hoping is to learn from those experiences and generalize. So we kind of have, there's a lot of things about domain-specific solutions, and we're kind of bottom up in parallel looking at a bunch of things to doing something that will work for each of these. And then over the next year's project is, how did that work? What did we learn? Were there common things across them, and try and build up that way? That's the approach that we're taking. I think some of the other centers are actually doing domain-specific languages, so there's a separate language for each one. But that's what we're trying. But it's been, working really closely with a domain expert has been very helpful. Is because people will get together and argue what the people want. What do programmers want? Well, we could go talk to an expert and ask them, and often it's a very simple. What they want is pretty easy. We came up with a very complicated thing. Yeah, but that's the kind of. Did that answer your question?
Specific question. This is
Question for answer, please.
There's a question from God, I think.
I'm sorry. Wait, I'm sorry. I have.
Where?
NC State.
Okay.
NC State. Is there any particular reason that you've excluded applications from bioinformatics?
Why have I excluded bioinformatics? Because I hate bioinformatics. No. It was, by the way, this is 20% of our project right now. So what we just did was kind of found people geographically nearby, who we could meet. We met with other parts of the campus, and we just didn't always find the right person. There are many other things that would be worth putting up here. We don't have computer games up there, for example. And we just, on the Berkeley campus, somebody nearby who actually wanted to work with us on this problem, and that was the way we have it. But I think there are many other areas that we could expand. If we had more money, plausibly, we would probably add more apps, that complement this in a way. And I think bioinformatics would be another really great area. I think, it's, you just, as long as it needs a lot more cycles, either more cycles in a small form. You're not happy. If you're happy with the way computers are today, we probably don't want to talk to you. So that's the primary requirement, and I'm sure there's more. And we just want to complement it in something that would be complementary to what we had. I'll try this side. Yeah.
So, as someone who would love to have 1,000 cores in my laptop for $1,000, I'm a little bit worried. How much do you think that the future of cheap, massively parallel chips is dependent on how well the gaming industry programmers can master massive parallel?
And the question was 1,000 cores in gaming. Well, the good news about the gaming industry is, they'll do almost anything to get performance without any elegant help. Just hire younger people, give them pizza, 100 hours a week, they'll get the thing done. I think, there's this, historical perspective. When I visited Bell Labs a long time ago, maybe 25 years ago, at the time, they quoted some famous person saying that in my lifetime, there have been 3 revolutions, and it was radio, television, and computers. And each time that happened, they said it was going to change the world and radically change education and bring people together. What happened for radio and television, it all came down to entertainment. I predict that the big impact of computing will be entertainment based on, so that was, he said that a long time ago before any of these things happened. So, I think entertainment isn't a terrible application, right? It's not a terrible thing. I think there's some evidence that some of the things that we call entertainment actually provide educational value to children growing up. That instead of passively watching television, you're interacting. That's not necessarily a bad thing. So yeah, I think entertainment's going to play a big role in the use of computing in the future. I even remember when I had friends who didn't like a mouse. They thought a mouse was inefficient. They thought that they could move the keys on the screen using keys rather than the mouse. The mouse was for wimps or something, right? I thought the mouse was fun to use, right? And so I can imagine that the user interface of the future is going to be a lot more fun to use. And then some people will argue, well, it's really no more productive than Emacs, But I think that would be okay.
BI.
Yeah, that's the response. Anybody out there in other geographic areas want to ask a question? I gave you a chance. All right. Is there? Okay. Yeah, if you don't get the microphone there, I'm not going to hear you.
Hey, can you hear me?
Yeah.
Cool. One thing that you talked about a little bit is the idea of education and teaching more sort of parallel concepts. One thing I'm kind of curious about is I know one thing that we kind of do a lot now is we focus on the sort of productivity layer. And, you know, we want to teach people languages that, you know, help get people jobs or that make computing more accessible. Are you saying that we should sort of do a shift to more efficiency layer programming or courses, which sort of, I don't know, seems like it would tend to shy away from skills that you might need in, you know, the workplace, and might make programming a little bit less accessible?
Yeah, I think the question had to do with languages and getting jobs and stuff like that. Well, I think that's the last thing computer science professors think about. There's this famous quote that says, "Moving a curriculum, changing a curriculum is as easy as moving a graveyard." You know, and that's the right thing. Boy, we change slowly. You know, every decade or so we change programming languages, right? So we're not like on top of. We don't leap from language to language there. So I mean, I think Java is probably the most widely used programming language, but there are still people who teach C++ and C and other languages there. So we move relatively slowly. I think at least as researchers, a question of can these highly productive programming environments like Ruby and Scala and others like this execute very efficiently on parallel computers and clusters of parallel computers? I think that's an open research question that we could work on. If that's true, then I personally would see the benefits of us as a field moving to a more modern language with these, you know, wonderfully productive programming environments that would let, you know, sophomores, freshmen who are trying to decide whether they want to study, you know, what they want to study on campus, do something amazing that they can show their parents, right? They can create their own run internet service that really runs with a great user interface and stuff that environments like Ruby on Rails provides, or probably the Scala and Lift things, and be really interesting computer science programming languages, and be parallel. But our field is so far from that vision that I don't even know how to measure the distance right. Getting people to think about giving up Java in the undergraduate curriculum and teach a more recent language and framework like Ruby on Rails, that would be, you know, that'd be revolutionary for that to happen. So it's we have a long way to go there in the productivity languages. I would say for computer science students, people who get a degree in computer science, at some time, besides, you know, this potentially extremely exciting first course of a very highly productive language where you can do amazing things, is later on getting into the nitty-gritty lower layers of the system would be, my guess would be good for you. Just like I believe you should study computer architecture. I think it's a great topic. I think everybody should take a course in computer architecture and all buy brand new textbooks. I think that would be a great idea. Because I genuinely think it's good for you to understand underneath the covers what's really going on. And similarly, I think lower layer, less productive but highly efficient languages would be good for you too. Okay, I'll try the middle.
Yeah, so I had a question about if a while back it seemed like the process was getting faster and faster, and the memory hierarchy was not keeping up, and so you were thinking about
that's true.
But now the clock speed is not speeding up as fast. Does that how is that going to affect that particular side of the battle between the
Well, the flip side of that question, although what you said is true, the flip side of the question is we're adding cores faster than memory bandwidth is improving.
So it's just as bad, it's just a different kind of bad.
Yeah, but the reason it's bad is what we've done is we surround the processors with a lot of caches to make sure we don't go to DRAM. And this is kind of a stable point. There's no need for tremendous bandwidth from DRAM because processors have all these caches around them. So the people I talk to believe if we really could figure out how to use 1,000 cores or 100 cores and we needed a huge jump in memory bandwidth, technically we could do that, but for that to happen, that would be more expensive than the current interfaces right now. So the DRAM is a commodity industry like pork bellies right now, and the prices fluctuate a lot, so it's a very conservative industry. If there was a case to be made that with, we need 5 times as much memory bandwidth, I believe technologically we could do it, but right now we need to show that there's some program, if you were to build a 100-core system, there's a program that could take advantage of it and sell. Right now, you'd bet against it. Right now, you'd say, no, the only thing people care about from DRAM is capacity, and cheaper is better, as opposed to the performance matters. So that needs to innovate, but I think, we can. There's good ideas out there if we can make the case. Up there.
Yeah, I was wondering if just as the caches, I mean, if you are a programmer, you don't worry about the cache normally, at least. Can you do something similar with parallelism? That you just program sequentially, don't worry about it, and then the compiler dissects everything and makes it beautifully parallel, optimized for the processor you're working on.
Well, that's your question is the reason why it's important to buy textbooks. Because part of modern textbooks is they have the history of the field in there. And that particular premise is about a 1970 premise. It's a great premise. It was really good that was investigated as a premise that can't compilers just automatically parallelize. But I think the case is pretty clear on that. I would say, I was saying earlier today, I think the future, we should be thinking of 100 cores as researchers there. But right now what you can buy is 2 or 4 cores or maybe 8 cores. Plausibly in that time frame, that would be an interesting startup company, is let's try and get some benefit from old legacy codes out of there. But I think there's a lot of data that suggests that maybe from 8 you could get 2 or 3, say, on average, but not that this will solve the problem going forward. That would be phenomenal if that were true. But we've got a lot of people spend a lot of their lives proving that doesn't work. Alas, betting that let's see how far we can go with that idea and giving up. Yes?
So when you think about 100-core chips, do you think about all the cores being the same, or do you think they'll be pretty heterogeneous?
Yeah, so the question about the 100-core chips, there's a bunch of people not only is it an interesting idea, people are building products that are trying all these things out. So the cell processor is an example of a heterogeneous design where there's 2 different instruction sets and a bunch of one and one of the other. So I think there's arguments technically about, because of Almdahl's law, about some things aren't going to be parallel, that you might want to have some number of fast cores. I think most computer architects think it ought to have, and by the way, and software people hate this idea. It's hard enough. You're telling me we have to make everything parallel and scalable and correct. Now you want to throw in heterogeneity. Yeah. What are you, nuts? Okay, but if we kept the instruction sets the same, that would help, right? We don't think we should just throw out instruction sets that are different for capricious reasons. So yeah, there's an argument that it's going to be heterogeneous over time. I think as we'll see, right now there's 2 or 4 or 8 cores, and if you're going to do that, you probably keep them all the same. If we really end up at 50 and 100 cores, we'll start seeing more heterogeneous designs. There's this argument that GPUs are heterogeneous, that there's the standard processor and there's the GPU with its separate memory system like that. That has something to do with how you construct computers where you buy something from somebody else. I believe those things will get closer together. But GPUs will be different from the thing that runs the operating system. Yeah, so I think there's a good case for heterogeneity, but kind of cost, performance, power, benefit. The programming, how are we going to do that without making the programming even worse is the challenge that people need. But I think it's likely to happen.
Another remote question?
I hope you can try her, yeah. Yeah, I'll have it's like me and arguing with DARPA. Well, either I'll get funding or I'll retire before the problem.
Another question from NC State?
Yeah.
Yeah. Just wondering, don't we need more than 10% efficiency programmers? And the other part of that is that doesn't the operating system get in the way? We now have general purpose multi-core CPUs, but we have the operating system only doing thread parallelism, and what we really need is application-specific parallelism, and the GPU is an example where the application programmer can get out and it's a heterogeneous process, but they can get out and code specifically for their application and take advantage of the parallelism where the operating system not getting in the way.
Yeah, I would agree that I think we're going to need innovation in operating systems for sure. And in terms of 10% of why we said 10% of the efficiency programmers, we've been teaching this parallelism class at Berkeley. It's hard stuff, right? Right now, this low-level details, not everybody gets it. It's not like, well, if you just give a lecture, they walk out of the room and they can program this. Not everybody, this is a hard thing to understand at this low level of detail. So maybe we can build better machines and languages so we can expand the group. But I think right now, if, the broad set of programmers in the world, people who write, Java 2 Enterprise Edition programs, if you call those programmers and that whole set, if we could get 10% of them comfortable with parallel programming, that would be great.
From Duke.
Okay.
Hi, just wondering, how difficult would it be to port current cluster-based programs that run on a variety of machines into a parallel architecture?
Yeah, the question, that way, since clusters have to overcome really long latencies, I think they should run pretty well. So far, and I think the fact that clusters, there are parallel programs that run well in clusters, that's a reason why I think the server part of the equation is more believable, optimistic. But so far, there's not very many things that would run on clusters that you'd say, boy, I just can't wait to run that on my laptop or on my cell phone. But yes, absolutely, if you can, there are things around there. And that, there's reasons for optimism in that there are things that run really well on clusters today. But so far, those haven't been the exciting applications yet. All right, so I was going to give myself a chance to try and do this thing, and so I'm going to switch gears here. All right. Oh, I got to get to the right point here. Okay, that's all right. We'll see how far this goes. All right. Okay, so the argument I'm going to try there's argument for a multi-core performance model is that, like I said, there's no consensus on multi-core, so it's pretty hard for programmers to figure out what they're doing and how well they're doing in particular. In particular, having somebody who understands these new architectures as well as new algorithms, it's not very many people like that. So what we did is a performance model that works across all of these various architectures pretty well, and I'll show you how that works. But these are all dual socket systems where the clock rates vary a lot and a lot of the microarchitecture details vary quite a bit, and I'll show you how that works. So we're focusing on these dwarfs that I talked about earlier, and what we're talking about is what's called bound and bottleneck analysis, which Amdahl's law is an example of that. So we're not trying to get exact prediction of how fast it goes. We're trying to predict where the bottleneck is to going faster. And what we're going to give an example about floating point example codes today, even though I think the idea is broader than that, but this is the example that we'll show you. So one of the key performance metrics we think is going to be the DRAM performance we talked about earlier. Right now, a lot of things don't fit in caches for these dwarfs. And so getting stuff out of DRAM is going to matter. So we're using a term that's going to be a key way to measure the programs in the architecture called operational intensity. And that's the average number of floating point operations per byte that goes to DRAM. So every time you get a byte from DRAM, how many floating point operations do you do? What's that ratio? That's going to give a lot of insight. Okay, so with that, on this log scale of performance in gigaflops on the y-axis, a question is, we're doing this bound analysis. What's one of your limits? Well, not surprisingly, for a particular computer, there's a peak floating point performance for a computer, and that's that red line. So you're not going to go faster than that on a particular computer. Now, it turns out you can also plot the memory bandwidth, and that's because I didn't show you what the x-axis is operational intensity. So operational intensity is the flops per byte, the floating point operations per byte, and the y-axis is gigaflops per second. So if you get the ratio of those two, you get gigabytes per second, and that's the memory bandwidth. So what's the memory bandwidth of the system? So that's that slanted curve, the red part of the slanted curve. And so what we're saying is if you characterize your kernel by this operational intensity, you can't get above the red and blue lines. So we call that the roof line. So that sets the limit to how fast you can go. So if you give me a computer, I can tell you the fastest you can go just from those two pieces of information. And now what's interesting here is that ridge point, where the roof line bends there. That's the minimum point the minimum operational intensity you need to get the peak performance. So that ridge point turns out to be an important characterization of computers that you might look at, because depending where that ridge point is, it's going to be really hard to get the peak performance or really easy. If it's over to the right, you have to have very high operational intensity, lots of flops per byte to get the performance. And if it's way over to the left, you don't need very many. And generally, it's harder to get a lot of flops per byte than, it's harder on the right than it is on the left. So particularly, you tend to use the word compute bound and memory bound. So if the operational intensity of something is over there in the flat part of the curve, that's considered compute bound. And if it's the slanted part of the curve, it's memory bound. Okay, so this is pretty simple analyses, but give you some idea of what computers like. So the question is, well, that's kind of interesting. What does a real roofline look like? And what are the operation intensities of real kernels? Next slide will answer that. So here's 4 different computers that I talked about earlier. The Intel Clovertown, which a bunch of you are using, has a really high ridge point, way over to the right. So you need a lot of flops per byte to be able to get to it, even though its peak floating point performance is very high. This is a log scale here. It's the fastest in peak performance. The AMD Barcelona, a little bit easier to achieve ridge point and almost as high performance. The Cell, that IBM Cell, much lower peak performance, but its ridge point is much further over. And then the Sun Victoria Falls, lower peak floating point performance, but the ridge point is even further over. So depending what the operational intensity is of particular kernels, maybe Cloverton's fine, right? Or maybe you need Victoria Falls. So here are the 4 that we looked at. And so the operational intensity is flops per byte transferred is generally 1 or less. So that means the ones with the ridge point over on the left, it's a lot easier to get the high performance. And as you can see where those kernels are, even though the peak performance of Cloverton Barcelona is much higher than Cell in Victoria Falls, its actual performance for those operational is much less. So kind of, if just for this part of the talk, a standard way for marketing computers is to give the peak floating point performance. Well, that's, not shockingly, that's a little bit misleading, because for a whole bunch of programs, you can't ever get up at that performance because you need too many flops per byte to be able to achieve that. So that's the first part of the roofline model. And now, so what happens if you've got these programs and you're nowhere near the roofline? Can this model be helpful as well? So it turns out what we can do is what we call ceilings. Is that if you looked at the programs and the parallelization that goes on, there's actually some limits that you can't go through the ceiling if you don't do this optimization. So one example at the top is multiply add imbalance. If you're doing floating point performance, most computers are designed to get the peak performance, you need an equal number of them. For a bunch of the computers on the slide, you need the SIMD execution and do lots of things in parallel. If you don't have the SIMD optimization, you can't get above that ceiling. And finally, instruction level parallelism, how many instructions you issue at a time. If you don't have instruction level parallelism, this sets a much lower limit. So that's kind of a computational ceilings, that if you don't do those optimizations, you can't possibly get there. There's also memory optimizations on the diagonal line. A big way to get performance is prefetching. If you don't do prefetching, that lowers the balance. And if you have one of these architectures that have separate sockets and separate DRAMs, you better optimize the placement of memory so it's near the DRAM near your socket, otherwise your performance lowers. So if you think about this, these 2 slides with these optimizations ceilings that you can't cross, you get diagonal ones and horizontal ones. And why is that useful? Well, then as you place the dwarf that you're worrying about, that you can know, in this case, it's in this region. Don't waste your time optimizing multiply adds, SIMD, ILP, because you'll never get there. You need to worry about the memory performance. That's what you need to be working on. So spend your time working on the memory performance, because anything you do there won't really benefit you. Okay. So this is the basic idea here is that this really simple to explain model that looks at the limits from the architecture can give you some insights about which architectures are going to be easy to use and not, and which optimizations in particular you should be worrying about when you're doing that. So the current issue of Communications at ACM has an article about this. This is my quick advertising tour of that. We think we've done it, some other people have done it, and with other computers, and it's worked well. We think this isn't limited to floating point. There'll be others, and there's more architectures and kernels than we can work on, so we'd love for people to do that. So let me wrap up the talk, and why are we doing this? Because we just can't, we have no choice, right? We can't build the 100 watt, 50 gigahertz thing. Amazingly enough, the whole industry has bet its future on this problem that many people have stubbed their toe on. So what an exciting time we live in. The once-in-a-career opportunity to reinvent the whole hardware-software stack. This will not come along again. I don't know when the last time it happened. Where you can, if you can solve this problem, you can change the instruction structure, operating system, languages, compilers, change the whole thing if you can solve this problem, because the whole industry's future is hanging on it. So this is the thing that researchers should stand up and salute here, right? So the failures isn't the sin. It's the sin is not trying. And so the final question here is: you're going to be part of the problem or part of the solution? And I think that's it.